In this week, we will talk about time response. What is time response? Firstly, we should explain it, okay? In whole dynamic systems, the time dependency determines the response of its states. Okay? What is response? Just remember the previous week we have talked about the DC motor or mass spring damper system. The state is the what, the position and velocity values, right? And so the time response is the time series output of these position and velocity values. Okay? Responses of its states outputs. Okay? And so in general notion, we can set the proper responses for a given system. Okay? And so, in order to do that, we need to set time response. Okay? This is just like this one. If we have the time and it depends on the x in here, okay? And so we are calling time response. Okay? That's it. And so using the Laplace transform, we can take the effectors of the system known as pole, zeros, and time response or system response. This three definition gives us the effectors of the system. Okay? And so if you want to design any system based on these rules, especially for the transfer function, and so we need to check the pole, zeros, and its final or beginning response of it. Okay? So output of the system can be summarized this one. Output of system is generally divided by two responses: forced response and natural response. Okay? And so, what is that? Anyone knows the forced or natural response from the system dynamic lesson? Anyone? Okay. And so, we will talk about it, but especially for this system, just remember that we have maybe a controller or the plant just like this one. S plus 2 divided by S plus 5. Okay? And so, this can be rewritten as 2 divided by 5 S plus 3 divided by 5 S plus 5. Okay? And so this can be inverted, or can be inversed of the what the Laplace transform can be applied on this system. And so we have the one step and we have the exponential response of it in here. Okay? So For the definition of these terms, we need to talk about firstly the poles. What's the poles of this system in here? CS, S plus 2, S plus 5. What's the poles? No, this is the 0. For the poles, this is pole, this is 0, and so we have S0 and minus 5 are poles of this system. Okay? And so it determines to the what? Determine the characteristics of responses. Okay? Not the 0. Especially for the pole, it's too important to create the R time response. Okay? Because we have the time constant and another parameters in here, and so it directly affected by the what? These poles. And so minus 5 and 0 are too important to determine what's the output response. Okay? And so what about the zeros? For the 0, just writing the same system in here, S plus 2, S plus 5, and so we have this term. Minus 2 is S, right? Because it's equalized to 0. And so this is the R0, okay? And so it determines to the what? Determine the output equals to 0 or not. In every case, we have this property or not. Maybe the time response is not affected by the selecting of the zeros, or the gain can be affected in here. We will talk about it. Okay? So, what is the force and natural response in here? For the system response, we have CS, which is equal to 2 divided by 5, S plus 3 divided by 5, S plus 5. And so taking the inverse Laplace transform yield us for this system 2 over 5 plus 3 over 5 e minus 5t. Okay? And so what is the forced response? This is the forced response. And this is the natural response. Okay? This... Huh? No, normal. We don't have any kind of normal response. Yes, this is the natural. Okay? And so, force response is equal to the what? We have this term. It's not time dependent. It's forced. Okay? And so, the natural response is directly related to what is time dependent property. And so, it diminished or increased. But we may have this property in here. Okay? These two responses are too important. And so, just remember the system dynamic lesson. We have S-plane. What is S-plane? Anyone knows that? S-plane? We have the transfer function in terms of what the Laplace transform. And so we have the unit, which we call it the S. And so S possesses what? The real and imaginary components. Okay? And so we can draw S-plane based on this term. CS, which is equal to the what? S plus 2, S plus 5. Okay? And so we can draw this term in here just like this one. the real part, we have imaginary part in here, and so what is the pole of this system? 0 and minus 5, right? And so if we have the pole, we should assign the cross term in here, and also minus 5, and we have the 1 0 in here, and so minus 2, we should give the O in here, just like this one. Okay? And so it directly related to the what, for example, this is the term of this term. We don't have any imaginary part in here, because we don't have this kind of root in here. Okay? And so M, J, W, okay? And so we have the minus 5, and so this yield us this kind of time response, K times E over alpha t, or this alpha is equals to what? 5, okay? This is the natural response. And so it represents to the what our drawing about the time response characteristics in here. The K, some constant, and so we can say that if we have the pole with the values of the minus 5, and so this system diminishing to the any state or the steady state. Just remember the system dynamic lesson, okay? So we should conclude that I should write everything in here, because in the later you will look at these notes, okay? If we have the poles at left hand side, so it always Ct going to 0 when t going to infinity values, due to what? E over minus alpha t, alpha positive, okay? Because it goes to the what? If t goes to the infinity value, and so this goes to the what? 0, right? Because of the exponentiation term, okay? And so at the origin, we have forced response, since it is like step 1. Anyone remembers that the step 1? Step signal? Step response? Yes, 1 over s. And so 1 over s has the pole of the what? The 0, right? And so if this is the 0, and so this creates the what? The forced response. Okay? Other ones, in that case, are nature. Yes. Okay? And also we should say that if the left hand side poles, it happens in here, and so left hand side roots yields or generates stable response. Okay? What is the stable in here? If we have this property, the natural response going to the what? Going to the 0. And so if we have any forced response, for example 2, 5, and so at the infinity we have the 2 or 5, right? And so it is stable. And so if we want to check our system stable or not, and so we will look at these poles, whether these poles are in the left hand side or the right hand side. If we have the left hand side poles, and so we have stable response. Okay? That's all.
Sir, could you please re-explain the first thing? If we have the poles at left hand side, always C of t goes to 0 and
Yes.
reaches infinity?
Yes, because this solution gives us to the what? This time response. And so exponential term alpha, for example, Ct is equals to the what? 1 times e minus 5t. If we assign the t is infinity, is going to the infinity, and so this going to the what? 0, right? That's all. And so if we check the S-plane in terms of the what? The poles, and so we can check the system is stable or not in here. Okay? So in section 2, first order system. Should be taught. Okay? And so what is the first order system? Suppose we have a system like this one. Rs is the input signal, and also A divided by S plus A, and the output signal is CS. Okay? And so what is the pole in here? This is the real and this is the imaginary part. And so where is the pole? Minus A. Right? Because we have a root in here. Okay? And so with, if we have these nominations, and CS is equals to what? Rs GS, and A divided by S plus SA. If the Rs is equals to the 1 divided by S. This is the unit step response, guys. Okay? Okay. And so if we have this condition, solving CS, taking inverse LP, and so we have this one. Ct is equals to the C forced, right, plus C natural. Okay? And so it yields 1 minus E over minus A times T. Okay? If you take the Laplace, inverse Laplace transform in here, this yields us this solution. Okay? Can you get it? Everyone? Okay. And so, which one is forced? Which one is natural in here? Yes. Yes. That's all. This is the rule. This is simple. Okay? So, but what is A? Anyone knows that? Yes, but we have the different name. No, we have different name. You are true, but we have different name in control theory or system dynamics. You should call it its time constant. Anyone remember the time constant? Yes. Okay. And so the time constant, or A, determines the transient response. So E over A T is equals to 1 divided by A, which is equals to what? E over minus 1, which is equals to 0.37, okay, or 37% for a given signal. For CT, and so the CT, which is equals to what? 1 minus EAT, and T is equals to 1 divided by A, and 1 minus 0.37, and so this is equals to 0.63, okay, or 63%. And so we can define this as 1 divided by A, which is equals to tau, okay, and this is the time constant of the response, okay. So this A generates to the what? The main shape of the time response in time, okay, and so this is a constant, and we can analyze the R system based on this notion, this idea, okay, how our system is fast or slow. This is the indication of the what? These terms, okay. If we have a pole in the first order system, which we call it to the what? The time constant, okay. And so
I have a small question. Sorry. What do the percentages mean? 37% of what? Is it an error or is it?
no, it's not an error. It's the level of the what? Our time response for a given system, for this system.
The closer we are to 100%, is that?
I should draw all the things in here, okay? This is the time constant of the response, and so this fellow, what's your name? Baran. The time constant of the response to decay 37% of its initial values. What does it mean? If we draw these terms in here, just like this one, the T, this is the CT, okay, and we have the 1 in here. This is the time is going to the what? To infinity, okay, and so we have the different levels in here: 0.9, 0.7, 0.6, 0.5, and 0.1. Okay, and so assume that if we apply the unit step to our system, and so this system response is just like look likes to this one. This is the output of the system, okay, and so if this is true, we can condition or we can assign the new values based on the what? The time constant. What about this one? 1 divided by A. This is what? Tau, time constant. This is 2A. This is 3A. This is 4A. And so this is tau. This is 2 tau. This is 3 tau. This is 4 tau. Okay? Time constant. And so, what about this one? If we take these terms, and so five 0.6, and this one is equal to 0.63. Okay? In every system, based on this notion, if we have the unit step response, this yield us the 63% of the last response or the initial response of this term. This is the time constant. This cannot be changed. This remains constant. Okay? You get it?
So the area before the 0.63 is always unchanged.
Yes.
Over down, but not critically down.
Yes. In the first order system, this cannot be changed. Okay? In Turkish, arkadaşlar bakın, bizim response'ımız 1 ya, burada.
I don't speak
Yes, I know. That's the other guys in it. Bakın burada 1 ya. Bu 1 olduğunda sizin bu zaman sabitiniz arkadaşlar kesinlikle burada 0.63 değene kadar değil. 2 ise mesela atıyorum 2 çarpı 0.63. 1 ise bilmiyorum. Bu bizim sabitimiz. O yüzden zaman sabit diyoruz. In the last case, just see that and the initial condition, this one, in the last case, we have the 1. And so, maybe this is the 5. We don't know, the last case. But we sure about that. This time constant happens at the 0.63 times 1. But if we have the last response 5 times 0.63 happens at the tau value. This cannot be changed. Okay? This is the standard constant. No. Yes, but in this case, this one is 2. This shape always preserved for the first order system. Okay? You can change the 2 and 1, okay? But this does not change. Okay? This is the same for the first order system. So this value is the what? Is the 63% of final value. Okay? And so this is tau, and the tangential components of these terms, this initial slope equals to the what? 1 divided by tau, which is equal to the a. Okay? Because it's a 1, and so this 1 should be given in here. And so this drawing or the time response cannot be changed. Either we should derive the final state condition in here. If we have 2, and so 2 times 0.63 happens at the tau value. Okay? This shape always preserved. Call it time response. Okay? So, if this is true, and so we can condition the whole of these terms in here, just like this one. This is the settling time. Anyone remembers that the settling time? For A, or 4 times tau is the settling time. Okay? Settling times means that the final value times 0.98 values happens always in that time. Okay? It's closing to the what? Steady state values. And so it does not change for the what? For the first order system. This is a constant. Okay? And so, what about this one? We have the another conditions or the formulations in here. This is the what? T settling time. This is the time. Okay? This is the 2% of final value. Okay? Or 98% of initial value. If you push the system 1, and so this settling time happens at the what? At this one. And so what's the values of this term in here? 1 times 0.98, 0.98, right? This happens. This always be same for the first order system. You can choose the different A. Okay, 5, 10, 20 is assigned in here. But this shape cannot be broken. Always the same. Okay?
That's why we use percent.
Yes. This is the constant. But this constant represents the time shape. Time drawing in here, which we call it the time constant. Okay? So, but just remember that this is considered as the first order system. Which means that x dot minus ax plus u. Maybe. Or in transfer function, we have this kind of information in here. S plus a 1. Okay? And so us can be assigned to unit step in here. It does not change. But this is the first order system. But what about the second order system? You know it? Second order system? Guys? In section 3.
So I have one more question.
Wait. Yes.
The 98% steady state, this is universal for all the first linear operations?
Yes, but but for the first order system, not the second order one.
So as soon as we have a first order, it's always going to be steady stating at 98%?
Yes. This is constant. And so, what about the second order system? In second order system, we have this kind of property. If we have the input signal in here, just like this one, Rs1 divided by S, this is the unit step, right? And so we can assign or write the transfer function in here, B, but in the second order system, we have two poles. Okay? S square AS plus B. And it yields or the outputs of the CS. Okay? If we have, what happens if we choose the S over 3 in here? This is the third order system, right? If we choose, for example, 3, this is the third order system. What about this one? S over 5. Yes, fifth. Okay? So, in this case, we have these nominations in here, two derivative terms or two poles at characteristic equation, guys, in here. In this one, this can be represented with what? The GS is equals to the B S over 2 AS plus B, which is equals to the B S plus S1 S plus S2. But we don't know what's the values of the S1 and S2. Okay? But these two forms are identical in here. So, if this is the case, we can assign the system response in here. System pole, zero plot, and responses can be given in here. Okay? First of all, anyone remembers that the overdamped system? from the system dynamic lesson? Overdamped? Overdamped?
Is overdamped or it oscillates?
No, it's not oscillate because it's overdamped.
Also it's slower. So it's the one that's
Yes. Just see, if we have the input values in here, 1 over s in here, and for example, suppose that we have the system 9 s square 9s 9. Okay? And so we have the pole 0 plot S plane in here. This is the real part, this is the imaginary part. We have two roots in here, just like this one. If you calculate the roots of these terms, we have the one pole and another pole in here, minus 7, 85, and minus 1, 14. Okay? This is the direct calculation of these terms. These are the roots of the R system. And so, what is the time response for this system? CS, and this is the CT. Okay? First of all, this is the unit step, and the last values of these terms in here, what? 1 divided by 0. Okay? But what's the shape of this system? What's the shape of the time response here? This is overdamped. Just like this one. You cannot oscillate in here. See? This kind of response happens in here. Okay? Okay. So what about this one? Underdamped. Bottom.
oscillation.
Yes. Underdamped has oscillation part. 1 over S. And so we have, for example, I'm sorry, this is 2. This is 9. But in this case, 9 divided by S square 2S plus 9 CS. Okay? And so in this case, we have two roots in here, real and imaginary. But in this case, if you calculate the roots of these terms, and so we have the roots at this one. This is minus 1, and also we have imaginary components in here. One root in here, another root in here. Okay? This is j times square root of 8 minus j times square root of 8. Okay? Okay? And so this generates the output just like this one. CT, and this is 1, and so this is oscillate. I'm sorry. The oscillation comes from the what? Imaginary part, guys. Okay? The otherwise, this is overdamped. Okay? So, what about this one? See? Undamped. What's the meaning of the undamped? We have two imaginary roots. S square 9. What's the root of this term? What's the root? Yes. In that root, we have this one, and this one, and minus j3, and this is the j3. And so, it looks like to what? T, CT, and so it is the 1 and 2, and it generates to the what? This kind of oscillation. Neither grows or neither diminish. Okay? Yes, at some point. But we have always a frequency response in here, just like the sinus and cosinus. Okay? Neither goes to the what? The one values or goes to the infinity. We always oscillate at this response. Okay? Any question? Okay. And so we need to give a break for 10 minutes, and after that the general second order system should be defined in our system.